Hey, welcome back everyone. Today we're going to be working on the 2D dynamic programming questions from the LeetCode roadmap. So today we're going to work on the first 4 questions here. Just like 1D dynamic programming, 2D is pretty similar. We're just going to be pre-computing the subproblems results and using those results one step at a time to finally build to our answer. So instead of using a 1D array like in the previous questions, now we're going to be using a 2D matrix. So correspondingly, these questions are going to be a little bit more challenging, and it's going to need us to record a bit more information. So let's get right into it, starting with the first question, which is unique paths. So in this question, we have a robot on a m by n grid, and the robot is initially in the top left corner, so at 0, 0. So now the robot tries to move to the bottom right corner where the star is, which is grid m-1, n-1. So the robot can only move down or right at any point in time. So we're given 2 integers, m and n, which is the side length of the rectangle, and we want to return the number of possible unique paths that the robot can take to reach the bottom right corner. So this is a pretty common question in both math and computer science. So essentially the robot can only go in one of 2 directions at every point until it reaches a wall or a boundary. So if the robot is here, for example, it can only move right. So it can only move right all the way until it reaches the finish. So however, at the start, the robot has 2 different options. It could either move down or it could move right. So let's say we have an arbitrary spot here, for example, this blue grid. So at this cell, the robot could have come from the north, it could have come down, or it could have come from the left and it moved right. So at this spot, all we have to check for is how many ways it could reach the previous up spot or the previous left spot. So cumulatively, we can add these 2 spots together to get the number of ways we can reach this grid, this blue cell. So for example, if we want to look for this white cell, there's 2 different ways, so it can move right then down or down then right. So there's one way to reach this blue cell, there's one way to reach this blue cell. So for this white cell, all we have to do is add its upper neighbor and its left neighbor to get the number of ways we can reach this white cell. So we can use a 2D dynamic programming approach to store all the available ways we can reach every single cell and compute this one row at a time to eventually get our finish. So let's create our DP array, or matrix in this case. So DP equals to, it's going to be a 2D matrix. And for every spot, it's going to have at least one way. So we can initialize DP to 1. So DP equals a 2D matrix initialized to 1 for nothing in range n. So this is the width of the cell of the matrix, and for nothing in range m. And this is going to be the height of the cell. So now for I in range, we're going to iterate one row at a time to cover every single cell and check the number of ways we can arrive at every single cell. So now for I in range, starting from 1m, because we know that every cell on the topmost row and the leftmost column are guaranteed to only have one way, since the robot must go in one direction only to reach those cells. So we don't have to care about those. So we can start this for loop starting at 1, and we can start the second inner for loop at 1 as well. So for j in range, starting from 1 all the way to n. So dp at the current cell, dpij, this is going to equal to the upper neighbor, which is dpi-1j, plus the left neighbor, so dpij-1. So we don't have to care about array out of bounds here, because I-1 and j-1 are always going to be greater than or equal to 0, since I is lower bounded by 1 and j is also lower bounded by 1. So this never goes out of bounds and we don't have to worry about that. So after that, we checked every single cell to get the number of ways to arrive at the cell by adding up the upper neighbor and the leftmost neighbor. So after that, we can just return dp at the bottom one, which is going to be m-1, n-1. The question already said that for us. So let's try running it. Cool, that worked. Let's submit it. Nice. So that was a nice and easy warm-up for the 2D types of dynamic programming questions. Essentially, we're going to be storing things in a 2D matrix, something like this, and we're going to compute the result based on pre-computed results, which is, for example, I-1 and j-1, since we calculated those before we reached the cell ij. Finally, we're just going to return the bottom rightmost result, which is going to be m-1, n-1 for our answer. So the time complexity of this question is going to be O of m times n, because we're going to have two for loops, one of length m, the other one of length n. So let's move on to the next question. Longest common subsequence. So in longest common subsequence, we're given two strings, text1 and text2, and we want to return the length of the longest common subsequence. Or if there's no common subsequence, we can return 0. So a subsequence in this case is a new string generated from the original string with some characters deleted without changing their relative orders. So for example, ace is a subsequence of A, B, C, D, E. So notice that we don't have to have the subsequence be consecutive inside the previous word, because A, C, and E are previously not consecutive, but we removed D to be left with A, C, E. So a common subsequence of two strings is a subsequence that is common to both strings. So the subsequence has to appear in both strings. In example 1, this is the ace example. Text1 has ACE as a subsequence, and text2 is ACE itself. So that's going to be the longest possible subsequence, and it's going to be length 3. So we're going to return 3. After that, in example 2, we have text1 is ABC, and text2 is also ABC. So the longest common subsequence is obviously going to be ABC, and the length is 3 as well. So in example 3, text1 ABC, text2 is DEF. They don't share any common letters, so there's not going to be any common subsequence, so the result is 0. So in this question, to find the longest common subsequence, we can look for every character in text1 and every character in text2 and compare them. So for example, if we're looking at the character C here, we notice that there's a C in text1 and a C in text2. So once we reach this conclusion, we can look for all the characters prior to C to see how many of those are common as well. And that's going to be the longest common subsequence up to the certain point. So previously, there's going to be A and A here, so that's going to be another subsequence. So up until ABC and AC in text 1 and 2, we noticed that AC, or length 2, is the longest subsequence. So now we can move on to the next characters in text 1, next characters in text 2, eventually until we see that E and E are the same. So noticing that these two are the same, we can add 1 to our previous longest subsequence, which is going to be AC. So eventually that's going to output us 3. So in this question, we can use a similar approach to the previous one where we create a 2D array or 2D matrix to store the longest common subsequence at every point within two strings. So we can have the rows represent the characters in one string and the columns represent the characters in the other string. So let's say m and n, let's be similar to the previous question. So let's say m and n, they're equal to the length of text 1, and n is going to be equal to the length of text 2. So m is going to be the height of our 2D matrix, so going vertically for the columns, and n is going to be the width of our 2D matrix. So creating this DP matrix, we're going to say it's a 2D one, initialized to 0, because we don't know if there's any common subsequences at all. So initialize that to 0. So for nothing, in range the width, and we're doing n plus 1 here because we also want to consider no characters from any subsequence, from any string. So we're going to start from no characters all the way until all characters, so that's going to be n plus 1. Now we're doing the same thing for the m string or text 1, so for nothing in range m plus 1. So now after that, we can do a for loop to check for common subsequences or common letters in both strings. So starting with the columns, so for I in range, we can start with 1 because we don't have to care about the 0th letter. That's just for us to keep our array not out of range. So starting from the first character in string 1 and then looking for the same character in string 2. So for I in range 1 all the way until m plus 1, since this number here is non-inclusive. Now we can do another for loop to check every character in text 2. So for j in range, starting from 1 all the way to n plus 1. So now if text 1 at I minus 1, so we're doing I minus 1 because I is the first character, but the actual text is going to be 0 indexed. So we need to do I minus 1 here. Same for the second text. So text 2, j minus 1. So if these two are the same, that means, for example, we found that C is matching. So we're going to look for the longest common subsequence, not counting these two characters. So we're going to look for the longest common subsequence inside A, B, and A. In this case, we know it's going to be length 1. So dp I minus I and j, this is going to be 1 plus 1 representing the common subsequence here, the C's. Forgot the equal sign. So dp ij equals to 1 plus the maximum common subsequence before this character. So plus dp I minus 1, j minus 1. So else, if this is not the case that these two characters are equal, then dp ij is going to be the longest common subsequence we've seen up until this point. So suppose we didn't include this character C, then what's the longest common subsequence? It's going to be length 1. So we're using the case where these two characters are not equal. So we can just disregard the character in text 2 or disregard the character in text 1. So it's going to be the maximum of dp I minus 1 disregarding the character in text 1, j, or we can disregard the character in text 2, so dp I, j minus 1. So these are the two cases if we have a character that is the same in both strings or if not. So at the end, we can return the character on the bottom right of this 2D matrix, which is going to be returning dp m. We don't need to do n minus 1 here because it's already range m plus 1. So the last character is going to be dp m at n. So let's try running that. Cool, that worked. So let's submit it. Nice. So this question has time complexity O of m times n, where m is the length of the first text, n is the length of the second text. So basically we're going through 2 for loops to check for every character pair in the first string and the second string to see if any of these are the same. If they are, we can look for the number of common subsequence or common characters prior to them, so dp I minus 1, j minus 1, in addition to the one that we know is the same. So if it's not the same, then we're going to disregard one of the characters and look for the previous largest longest common subsequence. So in the end, we can just return the cell at the bottom right corner, which is dp at m at n. So let's move on to the next question. Best time to buy and sell stock with cooldown. So in this question, we're given an array prices, where prices I represents the price of a given stock on the ith day. So we want to find the maximum profit that we can achieve, and we can complete as many transactions as we'd like. For example, we can buy and sell a share of the stock multiple times, but there's a restriction where after we sell a stock, we cannot buy the stock immediately on the next day. There has to be a cooldown day in between selling the stock and buying the stock again. So we can't engage in multiple transactions, so we can only sell the stock if we have it, and we must sell the stock before we can buy it again. So there's only one instance of the stock. We can't buy or short multiple instances. So for example, in example 1 here, we have prices equals 1, 2, 3, 0, 2. So this is the trend of the stock. So the optimal transactions is to buy on day 1, then immediately sell on day 2, take a break on day 3, do nothing here, and then buy again on day 4, and then sell on day 5. So that's going to net us a profit of 1 here between the 1 and 2, and a profit of 2 between the 0 and 2. So cumulatively, that's going to be a profit of 3. So, and we're taking this middle day here as the cooldown day, or the rest day, between a sell and a buy. So alternatively, we can also buy immediately at the start, and then we can sell the 3. So right off the bat, we get a profit of 2. But however, we cannot buy the stock at 0 since there's a cooldown day after selling the stock. So that gives us a cumulative price or profit of 2. That's going to be less than 3, so 3 is still going to be the optimal. So in example 2, we see prices is just 1, so there's only a single price, which means we can't get any profit since there's no difference in the price, and we need the difference to create profit. So in this question, essentially at every day, we're given a couple of decisions. So essentially, if we have the stock, then we can choose to do nothing with the stock, or we can choose to sell the stock. But if we don't have the stock, we can choose to do nothing, or we can choose to buy the stock. So essentially we have a decision tree that is based on whether or not we have the stock at the current time. So if we do, we can buy it. If we do, we can sell it or do nothing. If we don't, then we can buy it or do nothing. So that is going to be our decision tree. And we can use a DFS method or depth of search to look through the decision tree. And we're going to use a 2D dynamic programming approach to store or memorize our answers so we don't have to look too many times on the same searched tree. So let's create a function called DFS. And what it's going to take in, it's going to take in the current day we're at and whether or not we're holding a stock at the current day. So let's call that variable holding. It's going to be a Boolean representing if we have the stock or not. And to call the function DFS, we can return DFS starting from the first day. And at the start, we're going to not be holding any stock. So this should be false. So in the function DFS, first we should check that I is in range of prices. If we've gone through all the prices and we pass the last day, then there's no more profit to be gained. So if I is greater than or equal to prices, we can just safely return 0. So alternatively, we should also create a DP. So this is going to be a dictionary in this case for our memoization solution, so that we make sure that we don't do the DFS on the same I and holding more than once. So if we've searched this before, so if the tuple of I holding is in DP, that means we've searched this pair before and we can just safely return it. So let's return DP on the pair I holding. Cool. Now, so we have two different decisions. We can do nothing, or we can buy when, okay, actually we can sell if holding. So this is going to be one option. Alternatively, we can buy if not holding. So these are options here. So we know that in both cases, we can always do nothing. So let's calculate do nothing. So do nothing. If we do nothing, we should just DFS on the next day. And then whether or not we're holding a stock is not going to change since we're doing nothing. So let's pass in holding as well. I plus 1 for the next day and holding. So now we should calculate our revenue from selling or buying. So let's create those variables, sell and buy. They're going to be initialized to 0. So if we're holding, then we have the option to sell the stock. So when we sell the stock, the profit we're going to get is going to be DFS. Remember that after selling the stock, we have to wait at least one cooldown day. So we can't buy on the ith day. Instead, we can't buy on the I plus 1th day. Instead, we can buy on the I plus 2th day. So we can do DFS on I plus 2. And on that day, we're allowed to buy the stock. So on that day, we're no longer holding. So holding is going to be false, which means we can buy on the I plus 2th day. And after selling the stock, we're going to gain the money that the stock is currently worth, which is going to be prices at I. So alternatively, if we're not holding a stock at the current day, so else, then we have the option to buy the stock. So the revenue we get from buying the stock is going to be DFS I plus 1. That means we can sell the stock. For example, we bought here. That means we have the option of selling the stock on the second day or sometime later, depending on that. So we have the option of selling the stock, which means holding is going to be true. We're going to be holding the stock since we bought it. And to buy the stock, we're going to have to pay the current price. So minus prices at I. So now after this, we want to make sure that we store our current maximum. So let's call that profit. It's going to be the maximum of do nothing or selling or buy. So whichever one is more profitable, we're going to take that one. And DP at I holding, we need to memorize this. So let's store that in our DP dictionary. And this is going to equal to profit. And then we can just return profit. So let's try running that. Cool, that worked. So that's this question, max profit. This solution is a little bit different than what we did before. Before we were always doing a bottom-up approach. Now we're doing a top-down memoizing approach where we have a DFS, basically a decision tree at every index I. and as well as whether or not we're holding a stock at the current time. So based on whether or not we're holding a stock, we can choose to do nothing or sell, or choose nothing or do nothing or buy. So this is going to be the 2D dynamic programming approach, since DP is going to store a tuple, and this is basically a 2D matrix stored in the dictionary here. So alternatively, there's another approach that is a bottom-up approach, and that's going to be a little bit more complicated to understand, but it doesn't require the two-dimensional space we have here. We have 2D space because we have the variable I as well as holding. So those are two different parameters. So there's another 1D approach, and I'll cover that really quickly here. So in this approach, let's go back to the description of the question. So first of all, we should know that if prices is less than 2, that means we cannot buy and then sell the stock, which means there's always going to be 0 profit. So let's get rid of that test case immediately. So if len prices is less than 2, we can just return 0. So now we're going to create a 1D DP matrix or DP array initialized to 0 for every price. So now in this approach, we also have to keep track of another variable, and this variable is going to be called the profit plus paid. So profit plus paid is the entire profit that we've made so far, plus the amount we paid to buy the stock at the current index. So for profit plus paid, we have to have paid for the stock. So at the start, let's say we can either pay for it at the first time or the second time. So we're going to try to buy at the lower price. So the maximum of negative prices, 0, negative prices, 1. So whichever one is less negative, that's the one we're going to buy it at. And we should also set dp1 to be the maximum of 0. So dp1 is the second time here. So either we could not earn anything, or we can buy the stock at the first time and then sell at dp1. So it's going to be max of 0 and prices 1 minus prices 0. So now we can do a for loop, so for I in range starting from the second index all the way until len prices. So basically for every day that we haven't covered yet, since we covered dp0 and dp1. So for the remaining days, first of all, we have the option of selling the stock, since we already paid for it with profit plus paid. So to sell the stock, dpi is equal to the maximum of dpi minus 1. So this is equivalent to us doing nothing. We just don't sell the stock here. We have the same profit as before. Or alternatively, we could sell the stock. So how much we earn is going to be profit plus paid plus the price of the stock at the current time. So prices at I. So this is going to be the sell option. Essentially, we're comparing whether or not we should sell based on how much we get from doing nothing and how much we get from selling the stock. So there's also the buy option. So for a buy option, we're basically calculating what profit plus paid could be if we buy the stock at a better time. So profit plus paid, this is going to equal to the maximum of itself, so we don't get negative. So profit plus paid. And the profit plus paid, so it's going to be profit plus the amount we paid. So the profit is going to be dpi minus 2. Since for us to buy the stock at the current time, we must have sold it earlier. So we can't use, for example, if we want to buy at this timestamp, we have to go back 2 timestamps to calculate the profit here. Since after selling it, there's going to be a cooldown day. So that's why we're doing dpi minus 2. And now we're going to buy. So buying the stock means we're paying for the stock at the current price. So profit plus paid, the amount paid is going to be negative. That's going to be minus prices I. So this is essentially the buy option. So after that, we can just return dp len prices minus 1. So this is going to be how much we can make on the very last timestamp. So let's try running that. Cool, it worked. Let's submit it. So this solution is a little bit better than the previous one since it only requires a 1D matrix, but the previous solution is also it's a 2D matrix, but one of the rows only has 2 dimensions because it's a holding could be either true or false. So it's basically the same space complexity. And I think that previous top-down memorization approach is perfectly fine for this question. This solution is a little bit more hard to think of and understand. So with this out of the way, let's move on to the next question, which is going to be coin change 2. So in coin change 2, we're given an integer array coins representing coins of different denominations and an integer amount representing the total amount of money. So we want to return the number of combinations that make up this amount. Or alternatively, if this amount cannot be made up of any combinations of the coins, we want to just return 0. So we can also assume that we have an infinite number of each coin, and the answer is guaranteed to be fit inside a 32-bit integer. So looking at the examples here, we have amount equals to 5 and coins is 1, 2, 5. So there's 4 ways. So we can't swap the order of these. For example, 2, 1, 2 is not a valid way. We need 4 distinct ways to make up the amount. So in this case, it's going to be 5, 2, 2, 1, or 2, 1, 1, 1, or all ones. So that's going to be 4 unique ways to make up the amount, so we output 4. In example 2 here, the amount is going to be 3, but we have only coins of value 2. So there's no ways to make up the amount, so we output 0. In example 3, our amount is 10. The only coin we have is a $10 coin somehow, so we can only create one way to make this amount, or we just use one instance of this coin. So we output 1 in this case. So in this question, this is a 2D dynamic programming question because we can keep track of how much money we can make for every amount less than the current amount and all the way up to the current amount with these coins, and we can introduce the coins one at a time. So we can create a DP basically, so we're dpij. This represents the number of ways to make up j amount with I coins. So I could start at 0. First of all, there's no coins, so the only value that can make up is going to be 0. So then we introduce the first coin, for example 1. We look at all the values that 1 can make up, it's going to be everything. And then we look at the coins with 2 coins, so introducing 1 and 2. And then introducing 5, and if there's more coins, we'll introduce them slowly, 1 row at a time. So that's going to be the main idea behind this question. So let's create the parameters, or the diameters of the 2D matrix. So m and n, these are going to be equal to the length of coins and the amount. So m, this is the number of rows, and n, this is the number of columns of DP. So every row, we're going to introduce a new coin to the mix and seeing how many ways we can make up these amounts. So now creating DP. DP is going to be a 2D matrix initialized to 0, since we don't know if we can make it up, for nothing in range n plus 1, since we can start at the coin value 0 all the way until the value called amount. And the range should be for 0, for nothing in range n plus 1. Since we can also start with 0 coins all the way until we are introducing all the coins, all the way until m. So now we should know that we can create the value 0 with any amount of coins. So the first column of DP should always be 0, or should always be 1, because there's always one way to make up $0, since the coins are all going to be positive valued. So for I in range m plus 1, this is for all the rows, we're going to set the first column of every row to be 1. So dpi 0 is going to be 1. So now we can go one row at a time and introduce new values to our dynamic programming matrix here. So for I in range, starting from 1, since we don't need to deal with the first row, there's no coins, all the way until m plus 1. We want to go until m, since this variable here is not bounded, or it's non-inclusive. So now the coin that we're introducing here is going to be the current coin. So coin equals to coins I minus 1. Since introducing the first coin is coins at 0, so I minus 1 is going to be the first coin. So now for j in range, starting from 1, since we already set the first column of every row to be 1, we can just start looking at the second column, which is index 1, all the way until n plus 1, which is going to be the last column. So we should look at how many ways we can use this coin here to make up the current amount, which is going to be j. So first of all, we should make sure that j is larger than coin. So if j minus coin is greater than or equal to 0, then we don't have an array out of bounds issue. So dpij, this is going to be increasing by the amount dpi and j minus coin. J minus coin is the number of ways we can make up the amount j minus the current coin. So if we add the current coin to j minus coin, that's going to be the amount of ways to make up the current amount, which is dpi plus ij. So dpij, we could also not use the current coin. So if we don't use this current coin at all, then dpij should plus equals to the row above, which is when the current coin is has not been introduced yet, which is going to be dpi minus 1 j. So this for loop is going to loop through all the amounts and then all the coins, one row at a time, introducing one coin at a time until we can look at the total number of ways to introduce coins to make up all the amounts. So now in the end, we can return the cell on the bottom right corner, which is going to be dpm, not minus 1, dpm and dpn. So let's try running this. Cool, that worked. So let's submit it. Nice. So this question is a little bit more challenging. It's basically looking at the amount of money that we can make, as well as the number of coins. So these are the two different dimensions for our 2D matrix here. And we're going to look for the amount from 1 all the way to the actual amount, as well as the coins from using no coins to all the coins, introducing one new coin per row, and looking at how many new ways that coin generates with this if statement right here. So that's this question, and that's it for the first 4 questions in the 2D dynamic programming questions in the LeetCode roadmap. So thank you guys so much for watching. Hope you were able to learn something, and I'll see you in the next video.